As I said before, there's a direct translation between the kinematics of translational energy or translational motion and the kinematics of rotational motion. And here, these formulas in the middle column here should look very similar or very familiar to you. All of these we've seen before. Over here are the rotational equivalents. So, for example, distance, or x, is equal to velocity times time. Displacement, angular displacement, is equal to angular velocity times time. Final velocity is equal to initial velocity plus translational acceleration times time, with a constant translational acceleration. Angular velocity, the final angular velocity, is equal to the initial angular velocity times the angular acceleration times time, with a constant angular acceleration, and so forth. And so if you already know or have memorized these formulas, then these formulas should be pretty easy to remember. So let's use some of these formulas to work a problem. In this problem, we have a fisherman that hooks a fish, and that fish begins to pull a line out of his reel, as pictured above. The line starts at rest, and the line unwinds from the reel at a radius point of 4.5 centimeters. Now I know as line goes out, the radius will change, but we're going to assume that we can neglect that change in radius. As the fish goes out, an angular acceleration of 110 radians per second squared for 2 seconds. So he starts at rest. What is the final angular velocity, and what is the speed at 2 seconds? So let's take a look at how we would do this. First of all, let's write down what we know. We know that the r is 4.5 centimeters, or 0.045 meters. We know that alpha is 110 radians per second squared, and we know the time is 2 seconds. So first of all, what's the angular acceleration is equal to the final acceleration minus the initial acceleration divided by the time in which it took to get there. And so we've got, if we rearrange this, we know that alpha t is equal to the final acceleration, because this is equal to 0. And so if we put that in, 110 times 2 is 220 radians per second. So that's the answer to the first part. The second part says, what is the translational velocity? Or in order to calculate the second part, you have to calculate the speed, you have to calculate the translational velocity, and that's going to be equal to the angular velocity times the radius, which is the 220 that we just calculated, times 0.45 or 0.045. And if you do that math, you get 9.9 meters per second. The next question is, how much line, or how many meters of line, go out? And we use the formula theta is equal to omega 0t plus 1/2 alpha t squared. And again, omega 0 is 0. So this is going to be 1/2 times 110 times 2 squared, and if you do the math here, you get 220 radians of line. If you multiply, you remember that x is equal to theta r. That's going to be 220 times 0.045, or 9.9 meters of line. Now we have the same situation. You have the same reel, the same situation. The line is now going out, and after 2 seconds he applies the brake. and he achieves an angular acceleration of minus 300 radians per second squared. So he wants to stop the fish from winding out. How long does it take the line to stop? This is pretty simple. We know that the final velocity is equal to the initial angular velocity plus omega t, or alpha t. Now alpha here is changed to minus 300 radians per second squared. And so we know that the final is 0. So that means that omega theta minus omega theta divided by alpha is equal to t. And we know that from up here, we know this was 220, and the divided by 300, so t is going to equal 0.735 seconds. So it takes a little less than a second to stop that line if you have that kind of braking. Now here's another problem. Here we have a fly. Let me get the verbal part here. Here we have a fly, and he's sitting at the edge of this plate. The plate's radius is 0.15 meters. It's rotating at 6 meter rotations per minute. What is the total angular and linear distance traveled by the fly in 2 minutes? So, if 2 minutes of cooking, what is the total angular and rotational distance? So the angular displacement and the linear displacement of this fly, distance, not displacement, of this fly after 2 minutes. So we know that the rotational velocity is 6 revolutions per minute. We know we need to change that, and I'm not going to write all the numbers down. I'll just tell you that comes out to being 0.363 radians per second. Now I went ahead and multiplied by pi. R is 0.15 meters. And so, first of all, to calculate the angular displacement is going to equal the linear, or the angular velocity times the time, which is going to equal 0.63 times 120 seconds, which is 75.4 radians. The linear displacement is equal to the angular displacement multiplied by the radius. So that's going to be 75.4 times 0.15 is equal to 11.3 meters. So the little fella travels 11.3 meters. Now let's take a look at work and force applied to a rotational situation. Let's first take a look at force, then we'll take a look at work. Here we have a force applied to a wheel and inducing or producing an angular acceleration. The force required to spin a bike wheel, force is required to spin a bike wheel. The greater the force, the greater the angular acceleration produced. The more massive the wheel, the greater the size of the wheel, the smaller the angular acceleration. The closer you get to the axis to apply your force, the smaller the angular acceleration will be. So if F is equal to ma, we've seen that, that's Newton's first law, then F is also equal to m times the radius times alpha, or angular acceleration. Tau, which is the torque we were introduced to last week, is equal to F times the perpendicular distance, which is actually another way of talking about radius if we're talking about a circular object. Then tau, if you substitute this for F and multiply it out, you get tau is equal to mass times radius squared alpha. Rotational inertia is this concept, or this part of this formula. And in a situation where you have a single point or a single mass, the rotational inertia is equal to the mass times the radius squared. And it's important to remember that this formula applies only to a single mass or a single point mass. Now, if you have a frictionless table with an object on this frictionless table, it's attached at a pivot point with a radius of r. It has a mass of m. The force is applied perpendicular to r. It causes it to accelerate in this circle, and this is kept perpendicular. So this is what is meant by rotational inertia. Now, the reason I said that about a point is the only time that the formula that we're talking about, in most cases, mr squared, applies is if we're talking about a single point. It also applies with a hoop where there's a very even distribution around the radius. These other shapes represent formulas for the moment of inertia for various other shapes. So for example, here you have a solid cylinder that's rotating around its axis like this, and this can also be used for a disk, meaning that the L part is much smaller, so that the two ends are closer together. So its moment of inertia is equal to mr squared divided by 2. If on the other hand we rotate it around this axis, then you see it's ml squared divided by 12, and so forth. And so this is a table that I will allow you to refer to for problems related to this. So the net torque that occurs is equal to the moment of inertia times alpha, and alpha is equal to the net torque divided by the moment of inertia. So here's a common situation that you see in a playground. This is a merry-go-round, and a fella, it has a radius of r. He's applying a force here, and he's causing this merry-go-round to go around, and his force application is perpendicular, and it results in an alpha. This is supposed to be the man, not them and. Pictured below is exerting a force of 250 newtons on a 50 kilogram merry-go-round and a radius of 1.5 meters. What is the angular acceleration? And if you put a child, an 18 kilogram child, approximately in this area 1.25 meters from the center, what is the new alpha? So the first problem, first of all, again, we write down what we know. Force is 250 newtons. The mass of the merry-go-round is 50 kilograms. And R is equal to 1.50 meters. F is equal to mr alpha. So if we rearrange this, we can say alpha is equal to F divided by mr. So that's 250 divided by 1.5 times 50. And that's going to equal 3.33 radians per second squared. Now, what I did next is to say that you have two objects now with the child and the man and the disk. The first object, to do the second part of this problem, you basically take the same formula, but in the denominator you put that mr for the merry-go-round, and you have an mr for the child, and those two are added together, and so that's going to be 250 divided by your 1.5 times 50 plus 1.25 times 18. And if you do that, you get an answer of 2.56 radians per second squared. So adding a child adds an additional impediment to the circular motion and leads to a decrease in the rotational acceleration. Now we'll stop at this point, and when I come back, we'll talk about rotational kinetic energy